Chapter 1.3 is about finding limits by algebra. In Chapter 1.1 we took a very intuitive table graph kind of approach and just eyeballed things, but now we want a procedure for giving us exact values. Why do we care about limits? They help find the rate of change of a function as delta x goes to 0. Later we'll also see how they help as x goes to infinity for integrals. So let's talk about some basic limit properties, nothing ground shaking here. What's the limit of a constant? Like, what's the limit as x goes to, how about 29 of, what's another good number? How about 41? Well, you'd say, here's 29, here's y equals 41. What's the limit? How does 41 behave as x approaches 29 from either side? You'd just say the limit is equal to 41. Not a surprise. How about the limit of x as x goes to something like 12 million? No reason these numbers have to be small, right? So here's the y equals x line. Here's 12 million. You knew right where it was, right? And what would you say the y values do as x gets close to 12 million? Would you say the y values also approach 12 million itself? I would. So that limit is equal to 12 million. So the limit of a constant is that constant. The limit of x as x approaches something is whatever that value is that x approaches, but thinking of it as a y value. Let's get slightly more complicated here. How about the limit as x approaches, how about 40 of x plus 11? Let's graph x plus 11 as a y-intercept of 11. Here's 40. So what is that? What is x? What are the y values approaching as x gets close to 40? You'd probably say 51, right? Can we say that this is equal to the limit as x goes to 40 of x plus the limit as x goes to 40, as x goes to 40 of 11? Can I say the limit of a sum is the sum of the two individual limits? This being the result here being 40, because the limit of x as x goes to something is that something, and the limit of a constant as x goes to 40 is that constant. Well, it sure works here, and it turns out it works in general as long as the things you're breaking it up into, those limits have to exist individually. So we can say the limit of a sum is the sum of the limits as long as they all exist. What do you think about the limit of difference? Is that the difference of the limits? Turns out that's true as long as they all exist. Okay, so it's good for sums, it's good for differences. What else is there in the world? What's the next step? How about products? Limit of a product is indeed the product of the limits, as long as they all exist. And then after products, what is there? The limit of a quotient, and that is the quotient of the limits. As long as they all exist, not a big surprise there. But there's one more thing we have to think about, and as long as we're not dividing by 0, and that's the whole issue when we're doing difference quotients, right? So we have to be most careful when that's going on. So next we'll put these into practice.